Well, here it's all the trams. Yeah. It's very, very low to the ground.
It's scary because they're moving, and you don't hear them that much, and they're just like, walk right across right in front of them.
Yeah.
Yeah.
You only do it once. Oh, that mic's live too.
So we said we're standing or we're sitting? That's sitting. I think less. Otherwise, they might be distracted. Oh, you're next. You got to sit over there.
Yep. All right. Well, welcome. My name is Chris Malone. I'll introduce everybody in a second. But we're here today to talk about cooling temperature for next generation data centers and the IT that comes with it. So, as I said, I'm Chris Malone with Meta. I'm responsible for data center technology strategy. And with me today, I have my colleagues Paul Artman from AMD and Kelsey Wildstone from Microsoft, and also Steve Mills from Meta, who will host a panel discussion after we run through a few slides here kind of describing the problem. So this is sounds kind of an esoteric topic, coolant temperature, but it's an interface spec, and it really matters a lot for IT system design and data center design. And with the emergence of liquid cooling, there's a real need to get specific on what it is we're trying to design, both from the IT side and the data center side. So we have been working on this for a couple of years with our industry partners. And today we have Meta, AMD, Microsoft, and NVIDIA couldn't make it today, but they're aligned with this proposal. So this is a pretty good cross-section of some major hyperscalers and chip providers. And we're going to continue discussions over the coming months with other hyperscalers and silicon suppliers on this proposal. And okay, so why does this matter? So liquid cooling has been kind of an exotic topic in the industry for many years, but it's becoming, we'll say, an emerging requirement for ML systems in particular, and maybe longer term for general purpose CPUs. And it's even, I would say, more than an emerging requirement. The 1,000-watt GPUs are something that we can see coming in years to come. And so with that bulk power and that power density, there's a real need to move beyond air cooling, especially for these very large ML clusters that many of us are building. And so the important thing here is, again, I said the interface spec between IT and the data centers, and it's coolant temperature. So by coolant temperature, we mean the temperature of the fluid that's removing heat from the chip. So in the case of air, it's the entering air temperature to a rack, and here with liquid cooling, it's the temperature of the water or fluid flowing through the cold plate. And we want to pick a temperature that balances the headroom we need for future chip power growth and so on with the data center requirements. We want to strike a balance between very efficient data center operations and the lifetime of that data center versus the requirements for future chip generations. So we want an interface that allows for multiple chip generations in one of these very expensive data centers. And so we've kind of centered on 30 as a good balance. 30 represents a very good temperature for air cooling. A lot of very efficient data centers operate around 30 C air right now. And by choosing the same for liquid cooling, it simplifies the cooling plant and gives you a pretty efficient design and plus some headroom for future chip growth. But that said, this is an interface spec that kind of balances that efficiency versus headroom. To maintain that over longer durations, we're going to need to invest as an industry in thermal technologies and in particular in packaging to make that happen. So there are a bunch of packaging solutions that allow for better performance that are understood from an engineering perspective, but putting those into practice at scale is something that's going to require some concerted work over the next number of years. Okay, so I'll hand it over to Kelsey to provide some technical background on how we arrived at these numbers.
All right, Dobedin OCP. Again, my name is Kelsey Wildstone from Microsoft, and we've certainly been looking at the challenges of these CPU and GPU chips for a while now and the challenges that they bring. So this graph is something that we developed that shows thermal resistance of chip products over time. Now, thermal resistance might be a little bit of an insider thermal engineering term, but it is an industry term really to look at the measurement of an object or material and how it resists heat flow. So you can see the unit there is degrees Celsius per watt. If you take two temperatures and then divide that by the amount of power that you're trying to dissipate between those two temperature ranges, you can derive that thermal resistance. But basically, if you just think about it as like a heat sink, you're going to talk about how much that heat sink can will either resist the flow or really say how much heat it can transfer or what rate of heat it can transfer. So along the bottom here, we have a product launch year, and so each of these dots represent a chip, product. And some of the dots that we think we know about on the right have been removed, but you can still see that the trend line that they produce. If you're using a sort of standard heat sink and expecting to put more heat through it, as we put more wattage into these chips, you can see that the thermal resistance required for each of these chips keeps getting lower and lower and lower as that trend line keeps going down. And then we have this range here where we've identified liquid cooling required because there's only going to be so much heat that you can pull out of a heat sink with air going through it. And so we've defined this range of 0.03 based on looking at a 10U server tray and talking with many vendors about how much heat we think we could realistically get out of an air heat sink, and then we've just identified this range where you say there's a limit here, and after that point you're going to need some kind of cold plate or other liquid cooling solution. So we have these cones of uncertainty on the right here where again, CPUs being the blue trend line and orange being the GPU trend line. In the orange GPU range, you can see they're pretty well into that liquid cooling range. So we can see that is really going to be a requirement. The CPUs, a little bit less certain. We kind of show that cone there where it could maybe go up or down a little bit. Maybe not as sure. GPUs, pretty well there, but the CPUs may not be that far behind, right? Because it's like, they could dip down, and so, maybe a couple more years out, we see that come along. So liquid cooling, we know that this is going to be something emergent for, GPU, AI, ML platforms and next-gen IT systems. So that this really has significant impacts on both IC system design and durable data center design. And to talk about a few more of these trends, here's Paul.
Good afternoon. I'm going to talk about the general power trends we're seeing in the industry. These are not AMD specific. They're just kind of the trends we're seeing. What we saw for a long time in the CPU space is it was kind of flat. 140 watt CPUs for a long period of time, over a decade. We actually went from P3 at 30 watts to 120 watts with P4, and it was flat for a while. And then about 3 years ago, we saw the hockey stick, and we're seeing that CPU power is rising very quickly. So going from that 200 to 300 to 400, 500 watts very quickly. But what we generally see in the industry is the CPU power is starting to flatline, so it's not as aggressive as it's been. I think that's largely driven by the desire for end customers to have an air-cooled option. So we're kind of getting this artificial constraint where we're kind of limiting it to staying air cooled where it's possible. So we're seeing that be less aggressive. But the GPU trend, we started out with 300-watt GPUs, 400-watt, 500 watts, and that's really in the still linear power growth. So we're seeing GPUs gen to gen going up significantly. And we're seeing well past 1,000 watts. We're seeing 1,000 watts today, possibly, depending on which vendor you're looking at, and definitely projecting above a kilowatt, which really puts you outside of what you do in traditional air cooling. So this one's a little bit more complex now. So I showed the power trends as they kind of go up. And what I'm looking at is what is the temperature that I need to cool it. And as Kelsey showed, you have your thermal resistance, and that's kind of flatlining. It's hard to get your thermal resistance down. So the component temperature is a function of your approach temperature and your thermal resistance times power. So thermal resistance is staying flat, power is going up, so you're getting a larger delta T on your cold plate. And what's driving is a lower requirement for water temperatures. So if you're looking at a kind of CPU roadmap, these 40 to 50 degree water temperatures, 40 is pretty dominant today in Europe, is a viable for CPUs we see today. But as you project those out and what we're seeing on those power trends for GPUs, and we're seeing that's going to have to require to come down the water temperatures. And this does, Chris talked about packaging. This is with more aggressive packaging than we have today. We're still having a requirement that, for longevity, for an AI workload, I want to be kind of specific here. If you're doing a bunch of virtualized workloads, maybe you can stay in a liquid-cooled, a higher water temperature. But we're seeing a huge propensity for these scale-up AI models. And those are driving very high power at the GPU and interconnect. And those are going to drive the requirements for a lot of lower water temperature. So what we're kind of proposing is, as you look at a long-term roadmap for a data center, you want to have the possibility to drive lower water temperatures in the future, because you don't want to strand your power. So you bring all this power in there, and then you're stranding your capabilities.
All right. So that's sort of the technical data on the IT side. Let's talk about data center efficiency. So this curve, or this chart, shows on the vertical annual power consumption for chillers versus on the x-axis temperature. So the left-hand side of this chart is if you put your data center in a cold climate, right-hand side is if it's a warm climate. And so the three curves here show the 30C number in green, 26 and 21 in the other colors, just to kind of illustrate the impact of temperature on the efficiency of the data center. And you can see there's roughly a 20% hit as you go from 30 to 26, and then another 20% as you go from 26 to 21. So that's a pretty sizable hit to the efficiency of the data center that the industry's worked really hard to hit over the last decade or so. So this is the balancing act we're trying to strike. We're also looking at data center designs as an industry that use less water, so that is also an energy efficiency hit as well. So this is all kind of a balancing act, as I said, to design the right system with enough headroom into the future for the chips that we expect to come, but also focusing on efficiency. So just from a pure data center perspective, this image in the background is of a large-scale meta data center, and it's typical of hyperscaler installations around the world. We're talking about many megawatts, and the capex cost of these facilities is pretty high. So this is from an industry report. There was a global-wide spend on data centers of around $220 billion in 2021, and we expect that to more than double by 2030. So the capex spend is substantial, but I would say even more importantly, data centers are not as agile as our IT systems. We see IT systems turning over, especially in the ML space, annually, or every 2 years we get a new release. Data centers, on the other hand, take 2 to 4 years to build out. You have to assemble construction crews in the thousands to build these things. And the infrastructure is designed for a lifetime in excess of 15 years. So there's a real mismatch between how fast IT changes and what the data center, how the data center can respond. So, the thing is, we can always raise the coolant temperature. You can do that by, using less fan power, using less chillers, etc. But conversely, it's very difficult to lower the temperature of a data center, coolant. It often involves pretty extensive retrofits and so on. It takes time. So this is where, a clarity in terms of this interface matters. And if you look out in the industry now, there's a pretty wide range of what people think liquid cooling temperature should be. So like 15 to 50 degrees based on who you talk to. And from a design perspective, both on the IT side and data centers, that's really not helpful. So that's kind of why we're all here talking about tightening up that range to something that makes more sense.
All right, and hopefully none of you thought that you were going to escape today without a call to action. So what we're asking you to do is really think about, what we're saying here with this call to 30 degrees C at the server, because there's a lot of subsystems that can benefit from this alignment. Chris kind of opened with saying why this is important and talking about some of those benefits. But the chip roadmaps and packaging, we think that's the largest opportunity. But certainly, data center cooling subsystems and enhancements to extend this operating point for as long as possible, and even some heat reuse opportunities. So, liquid cooling is not really a mature thing yet, and so there's plenty of opportunities to standardize around this field. Certainly, we can come back and talk about, fluid standardization, pressure drops, or, flow rate per watt. But we really want to start here. And so what I would ask all of you to do is when you leave this room today, think about what you can do in your role in your organization to help us drive toward this 30 degrees C water temperature. So thank you, and we're going to do a panel now. You guys want to pull the
Nice. Pull up or stand?
Yeah, why don't you go ahead and pull up to the middle there.
Up.
Squeeze in there.
So they can see us a little bit better. All right, so thanks for that. That was very interesting. So the first question I've got is directed towards Chris. So why do you think that it's important to have this alignment between hyperscalers and chip producers now?
Yeah, so we touched on this a bit during the presentation, but I'll just say again, liquid cooling is really still in its infancy in terms of building it at a scale that we think we're going to need in a few years. So it's not, I don't think, beneficial just for hyperscalers and chip providers. It's generally useful for the industry to align on some standards, some ideas about how to implement these things to reduce the number of variables. Yeah, it reminds me of, in the early 2000s when enterprise servers were a thing, each enterprise server vendor had their own temperature specs. And yet, for a customer, all these vendors ended up in the same data center. So that was very confusing for everybody. It made it hard to build data centers that are efficient and predict things and so on. So there is something similar going on here, where there's a divergence in terms of what various folks think they need, but yet we all build data centers that fundamentally have some pretty similar backgrounds, and we use requirements, I should say, and we all use silicon that has very similar physical properties, so it's not all that different across the entire spectrum of data centers. So coming up with some clearer standards on this is going to help scale this technology in a more predictable way, and that should address risks in terms of the useful lifetime of data centers and being ready for future IT systems.
Yeah, and I build on that. I mean, to Chris's point, ASRAE came in 10, 12 years ago and said, hey, we're going to go define what ambient temperatures are. We went in there, did 32, 35, 40, 45. You had the idea of higher temperatures for heat, or not really heat reuse, it was really, the free air cooling. And then ASRAE went in there and said, we're going to define the water temperatures, but they're the facility water temperatures. as a chip designer, that doesn't help me. I mean, if you say design A2, I know exactly what to do. You say design a W27, I'm like, I don't know what that means. And so it really had to have some kind of alignment. And it helps internally also because as you're driving so aggressively in power, the people internally go, well, just turn the water temperature down. Just, we'll do 17 and then we can throw more power at it. And so, having alignment kind of, I can go back, well, no, we can't do that because we've all agreed that there's got to be a common set point.
Yeah.
Okay, all right, that's cool. So Paul, a question for you would be, in the presentation you had stated like 30C was kind of an ideal set point. So can you kind of go into a little bit more detail of why 30C is the best choice?
Yeah, as you look at, to Chris's point, I think if you look at the efficiency going to these going cooler just is really inefficient. You don't want to go to a chilled water and have a significant temperature impact. So we're looking at what is a reasonable trade-off between efficiency and temperatures, and as we looked at our roadmaps and kind of projected out, we AMD, NVIDIA, and everybody go, yeah, we think we can live with 30. It's aggressive. We're going to have to do some packaging. But there was a lot of that discussion around the legacy W40, and we're like, yeah, I don't see, if you're trying to do the warm water, that's going to be really challenging. And you can get there, but you're trading off performance. And really, you look at these models, it's, you really want to have max performance. Do you want to throw more power at it to get less performance? It seems counterintuitive, right?
Yep.
I can run the lower temperatures, and I'm going to take a lot longer to get it done, and aggregate, I'm going to take more energy.
And I think that bears repeating, too, that when we talk about the 30 degrees C, we're talking about the server chip. And as you guys have said, there is a difference between the data center side and the server side. And we know there's going to be some inefficiencies in the design based on, depending on what kind of design you do, there might be a couple degrees difference there. And so we know that we're going to have to run the data center a little bit lower than that anyway. So as part of this, when we're saying, 30 degrees at the chip, we're trying to say, hey, that's a sort of high water mark that we want there so that we don't have to keep trying to drive the data center even colder. So it gives us some bounds to work with.
Yeah, I think it also, by talking about the temperature on the IT side, it gives the data center operators some flexibility in terms of how they want to approach the system design of the data center. So you might have a much lower approach temperature and spend more money on it, or vice versa. So there's some flexibility in terms of data center design. But I think it's also just important, to remember, 15 years ago, the typical data center PUE, which is a metric for efficiency, was 2.0, meaning, for every watt of IT power, we spent a watt on running the data center. And we don't want to move back to those days by just throwing a ton of power to cool, below what is reasonable to anticipate these future systems.
Okay.
And I would say, in general, we saw too, there was a huge trend in the industry of PU at 2.0 to undercool everything. So you're delivering 15 to 17 degree air temperatures. You're wearing a jacket.
Freezer box in the data center.
I don't need to be that cold. We're wasting a lot of energy. And then we push the bounds up to 27 might be a more reasonable range for typical.
Okay. So another question for you, Paul. So is this particular interface specification really focused towards a particular technology, like was it a cold plate or immersion or?
Yeah, the data that I show is around direct liquid cooling. We see that as the technology that scales out furthest. I think two-phase immersion has capability in terms of thermal performance. The problem with two-phase is it's boiling at 50. I need 30. So you have this big delta, and how do you get something that boils on the enough temperature? Yeah. The single phase just doesn't scale out to these kind of power levels. Really, single phase is probably in the order of air-cooled capability, maybe a little more density, but we're talking about really extreme densities that require direct liquid cooling.
Yeah.
Okay. So for the Kelsey, so when we showed the slides about as PUE gets worse as the coolant temperature goes down, right? So knowing that, right, why would you specifically pick like 30C as opposed to something that would be warmer
definitely.
than that?
Well, I mean, I think first of all, like we've kind of been saying is, the first thing we want to keep in mind is we're saying that we're selecting a lower coolant temperature just because we see it as a necessary step for the performance of the chip. So I think that's number one, is that we're saying like, hey, like that slide that I showed with, as the thermal resistance needed kind of gets lower, it's like you're going to get to a point where you have to do some kind of liquid cooling. The second part of that about the temperature is that there's, PUE is Chris said, is, one metric that we talk about a lot in the industry, where, we were trying to drive PUE down, and we saw in the industry a lot of people move to water, evap, right? And so we talk about free air cooling, and we evaporate a lot of water. Well, that makes our PUE look lower. But now there's a lot of talk in the industry about WE, water usage effectiveness, right? So how much water are you using in your data center? And you have to really look at both of those in order to sort of get a clear picture. So we might see PUE go up in some of these cases, but in a lot of design we're seeing water use go to zero, which has actually been more important in some of the communities in terms of sustainability. And then lastly, I would say, we had talked about this a little bit before. One of the newer metrics that I've seen is TUE, or total usage effectiveness. Because if you look at like a PUE metric, some of the things that are buried into that metric is like if you say in your server, you're running a lot of fans in that server. You also have the inefficiencies of your PSUs and all that kind of stuff. But just even looking at the fans, that's part of your cooling, but that gets buried into sort of the IT metric of your PUE. If we talk about liquid cooling, we're removing the energy from a lot of that fan use and putting it in the data center side. So it looks like the PUE goes up, but you really have to look at the whole picture to see where your actual efficiency is.
Okay, it's giving you some flexibility as well.
Yeah.
Yeah, I mean, so I agree with what Kelsey said. There is this move in the industry towards using less or no water at the data center side. So, that typically does mean more energy consumption. So it's this balancing act. And again, in picking these interfaces, we have to think about, how much durability do we build in? How much flexibility do you build into this new, multi-billion-dollar data center without going overboard? Because every degree that you lower that design temperature means not only more cooling, but more power that goes along with powering that infrastructure and so on. So, that's kind of the thinking that goes into this kind of spec.
Okay, right. So I guess another question for you, Chris. So are we ever going to see a 100% cooled data center with liquid?
Liquid cooled data center, yeah. This is a question I get quite often, right? It's kind of funny, like at present, I spend almost 100% of my time working on AI at scale and all those problems. But the reality is we are doing liquid cooling for systems like ML, not because we want to. We would love it if we could just stay with air cooling. It's tried and true and so on and so forth. We're doing it to unlock technical performance. So the power density on the chip, the bulk power, the need to compact these systems for better network performance is what's driving us to do this. And ML is an incredibly important topic right now, but it represents a fraction of the total power that goes into the typical data center. So there's really no driver to convert storage to liquid anytime soon. And as Kelsey showed, maybe we could see a move towards liquid with x86 sometime in the future. But right now, there's really no underlying technical or obvious business win for doing that. So, and I don't expect that to change for some time. So, no to 100% typically. I mean, there might be some one-off facilities that are super, super tuned for something. But, when you think about designing something for 100% either air or 100% liquid, you kind of lock yourself into an outcome. So that's one thing we're wary of when we make these decisions.
The other thing about 100%, is I think a lot of times when people ask a question like, hey, we're going to see 100% liquid cooled, they're thinking like at the server level. Like, is it 100% of the components in the server going to be cooled liquid cooled? Like, well, from a certain standpoint, if you look at sort of data center design, you could answer that as yes, because if you sort of want to do an efficient data center design, you put a liquid cooling plant, you're going to put that, cycle that facility water through your data center, and you're going to use some of that facility water to turn into air-based, cooling, because depending on how you're doing it, you're probably not going to want to install a liquid-cooled facility water plant and then also have an EVAP plant over here with free air. So you could look at it that way and say like, hey, even if you're taking some percentage of your liquid cooling load to the data center and turning that into an air mover, the data center perspective from the outside is 100% liquid.
Yeah, that's a good point. It just kind of illustrates how new this topic is, where we need to get really clear on some pretty basic principles.
Exactly.
A lot of data centers use liquid cooling, right, in terms of delivering a fluid to an air handler.
Yeah.
It's really this extra mile to the chip itself that's new for us. Yeah.
And you got to remember there's gigawatts of deployed air-cooled systems out there, right? The data centers are air-cooled, so that it's not a light switch. Where we're seeing, AI being the kind of tipping point, the spear into the data center that really drives that. But it's going to take a long time. We've been talking about liquid cooling 20 years. Yeah. I mean, Intel put it on the roadmap. If you don't remember, a long time ago, where they bifurcated the thermal profiles, and it's like, you got to be ready for liquid cooling. And everybody's like, ooh, I'm not ready. And now I think it's real. But it's going to take time.
Yeah, but I mean, like in your side too, you talked about the cost of going lower, right? Now that we've sort of seen this shift to trying to get the most efficient air-based systems, now we're saying, okay, well, we might need a little bit lower that chip, but it's going to cost a lot of money to put in new equipment. Whereas if you put in maybe a facility water plant and you use some of that to convert to air-based loads, it does give you a little bit more flexibility, because then you can take some of that and say, okay, now if I need to put some of that toward chips, you can kind of convert and direct all of that. But if you don't have that plant there, it's going to cost you a whole lot of money and time to put it back in later.
Yep, absolutely.
That's exactly right. And so that's another reason why 30 is kind of a nice balance point. As I said earlier in the talk, you've got the cooling plant that's delivering that fluid. It can be diverted for the air handlers to deliver the air cooling, and also to the technical water that goes to the chip itself. So that reduces complexity, so you don't have two parallel systems that you need to build out.
Yeah.
Okay. Chris, in your slides, you'd also talked about kind of the difficulty and the long lead times associated with updating the data centers compared to the IT cycle. So I guess it's a question kind of for you, Paul, since you're the chip guy here. What about how is the chip packaging going to be helping kind of resolve this problem as we go forward?
Yeah, as you kind of look at this, what you're seeing is that the dominant thermal resistance is the package. So in traditional air cooling, the heatsink was for performance, and you really didn't think about the packaging too much. And so as we look at the bottleneck being the package, this is where you start looking at how thin are you doing your die? What kind of enhancement on thermal properties on the die are you doing at IHS? Which is really the integrated heat spreader on top. It really makes it consumable. It's very resilient, but it's another thermal resistance. So how do we get thermal resistance down in the packaging is something we have to look at for sure.
Yeah, it's interesting. If you look at the typical x86 package right now, it looks the same as it did 20 years ago. It's a piece of copper, high purity copper on top of a silicon, and certainly there's been lots of innovation in terms of bond line thickness and tin materials and so on, but it hasn't really fundamentally changed for really good reasons. Right? That lid provides a lot of robustness for the chip vendors and for the integrators and the data center operators. So removing that lid technically makes a lot of sense, but it brings with it a lot of risk that the whole supply chain needs to understand better. But yeah, as Paul said, the bulk of the delta T, if you will, is from the silicon out to the package, right? So we're talking about many dozens of degrees C from that junction that matters to the lid of the chip where you put that cold plate on. So optimizing for that is something that we really need to focus on as an industry, because doing that at scale, getting that whole supply chain nailed is going to be a considered amount of work.
Yeah, I mean, I think one of the big things is the test and validation. Yeah. That whole process changed when in your assembly.
Yeah.
Well, I'm pretty sure the fundamental properties of copper and aluminum haven't changed in the last 30 years either. So.
Yeah, so it is kind of amazing that I guess the amount of resistance that's between, that little small space between the component and the copper, and then compared to the copper and the data center resistance.
Light bulbs, it used to be 100 watts, now a light bulb's 5 watts, but and now we're talking about 600 watts at really high density, right?
Yeah,
I mean, it's a few
and
components.
they just keep climbing.
Yeah.
I mean, the chip density has gotten pretty crazy.
All right, so here's a question for all of you. All right, we'll start with you. So, are you actually deploying any liquid cooling in your data centers now?
So not that we've publicly announced,
Okay.
but you can see publicly, you guys have probably all seen Microsoft has essentially funded or given a lot of money to OpenAI. You can see how much that ChatGPT has really blown up. I think they were 1 million users in about a week, and I think it was 100 million users in about 2 months. It was like setting lots of records for the most users. So. I'll kind of let you guys imagine what it's been like internally since November when that was released, and what kind of demand that's created, and the firestorms that we've been going through. So I'll just kind of leave that at that.
All right. Yeah, Paul?
Yeah, and we've done liquid cooling, not broadly. As you look at LCAP 10, Frontier, these big HPC clusters, multiple partners, we're doing liquid cooling. That's driven around density today. So it's a very, as we talked about, it's not super mature. It's been around, but it's very narrow what we're doing today. And I think everybody's trying to say, how do we broaden this and make it more consumable? Because it's really a hard consumption model at this point.
Yeah. I'll also say too, Microsoft, and certainly we talked a little bit about Emergent, and certainly Microsoft has been public about looking at that and investigating it. We haven't kind of announced some of the other sort of areas that we've talked about here. But I think you guys can infer that it's like, there's a lot of these technologies, and we certainly are trying to keep tabs on all of them.
Okay. Chris?
Yeah, so we announced back at the last OCP in San Jose and in the fall that we are turning a new data center design toward supporting liquid cooling with cold plates, driven primarily by this foreseeable future where ML, to unlock the performance and performance per dollar that we need, is going to need to have liquid cooling. So, it's certainly a very active topic right now for something that we see coming in the next few years at scale.
It's probably worth pointing out too that as you look at the ORV3 rack, as released, it has a manifold placement for a manifold, working on quick disconnect. So there are the elements that we're adding there to kind of get that to scale out.
Mm-hmm. Yeah.
Okay, cool. So, Paul, you're heavily involved in ASHRAE. So how does this initiative align with ASHRAE's kind of view of the future?
Yeah, so it dovetails real nicely. I've been working on this probably for about a year since I talked to Chris last year, and we're coming out with our next handbook. It'll be the end of the year, and then it's a little nomenclature. We're calling it secondary supply temperature. Not technical water supply temperature. There's so many acronyms in the industry.
Yeah, and I don't think we covered that because we said technical water. I mean, that was a point that was confused for me when we talk about technical water. It's like, what is that? And then you guys are like, it's ASHRAE. That's what's at the server chip. I'm like, technical water. Okay.
So, but the idea is we're going to go ahead and I think everybody's left on a 30. So that's kind of where we're looking, and then 40 and 50.
Okay.
And so we don't want to abandon those higher water temperatures, but we definitely want to have, again, the handshake that says facility water temperature is really useful, but it doesn't help me as a silicon, and so that'll be in the next handbook.
Yeah, I think working with ASHRAE is absolutely critical. Similar to what we did a while back with air cooling standards. The enterprise server vendors of the day were instrumental in basically sharing their view of what was coming, and there's an analog to be made there. Like the hyperscalers are kind of in the lead in terms of this transition to liquid, but it's a general trend. So I think this is going to be applicable to the data center, more broadly in the future. And getting ASHRAE engaged and getting those specs out is critical, because that's where the construction industry looks for guidance and design in terms of what to build out in the future.
I think so. It's one of the big things that we've said that we're trying to drive, with having this alignment with these companies, is to build on that standardization and to get more of that alignment in industry, and ASHRAE is certainly a partner in that. So, yeah.
Okay, all right. So let me ask you about like the risks associated with these, right? So, Chris, I mean, when you're looking out on this, right, from a risk standpoint, what do you think is the kind of the biggest risk in being able to achieve this kind of alignment?
Yeah. Well, I think building out liquid cooling at scale has a whole bunch of risks that need to be managed, and we're all looking at mitigating those risks carefully over the next few years. And part of it is the supply chain to deal with this in the many megawatts worth of capacity. It's easy enough to build 10 megawatts worth of liquid cooling, but if you want to dump 10x that, then you need a supply chain that's robust enough and diverse enough to deal with all the issues that come up. And then there's the operational complexities that go into running liquid on the floor, which there's risks to manage there, certainly. Yeah. And then in terms of the interface spec durability, the thing we really need to keep our eyes on is, as we move to the next gen or the next gen, and you move to a new semiconductor process, and all of a sudden the power density on the die goes up more than we expected, or in order to get the performance that we need to see generation to generation, you have to turn the clocks up, and all of a sudden the 1,000-watt part turns into a 1,500-watt part. Yeah. So these are real things, and it's new enough of an area that we really need to kind of watch that and invest, as we've said multiple times, into the packaging and thermal solutions that are going to allow us to continue to see these performance gains over time.
And what I tend to see, I've done this quite a bit in HPC, is the infant mortality is the problem, right? Did I do something wrong in manufacturing? I'm charging it wrong. I don't have the right additive. But it's extremely resilient when you get it going, But leakage can happen. I have a piece of braze fall off and get in the quick disconnect. Did I do something wrong in terms of my manufacturing? Lots of processing controls, but extremely resilient once you get through that period, and I think there's a lot of learnings we're working on.
Yeah, absolutely. I mean, I've heard about leaks as being a big thing. Anytime you hear talk about liquid cooling, it seems like the first thing that people talk about. Well, what about leaks? Well, I mean, it seems like from everybody I've talked to, the biggest risk there is like when it's initially sort of connected, maybe a disconnect during service, but typically once you have it there, it's going to operate more or less. And the other thing that you kind of talked about, is just the risk of these powers just keep going up, maybe beyond, and. Yeah, of course there's that risk. We're all trying to shake the crystal ball as hard as we can and kind of see like what's on the horizon, where these data centers are going to go. And so when you talk about a data center that's deployed for 15 years, we're trying to say like, okay, what's that 15 years on the horizon? I mean, that's a lot of crystal ball. Like that's really big. So we're trying to say, okay, we can select a temperature that we try to have some comfort in, and part of what we're saying is that getting this alignment is that then it gives us something to shoot for. So at least then we try to say, us in the industry, between even chip manufacturers, hyperscalers, that we try to stay there as long as possible and say, okay, for this generation, let's keep trying to drive that and squeeze as much as we can out of that instead of just keep hopping to the next thing.
Yeah, and I would say, these having constraints is very useful. This is the ML systems at scale is the ultimate system design problem, because you've got to balance the data center design, IT system design, network power. All these things need to be kind of weighed up against each other, all these benefits and trade-offs. And so this is where like some sort of stake in the ground about what we're going to design around is helpful for the team. With system design, every group that's involved should be a little bit uncomfortable and unhappy about what they need to design for, right? Or else we're probably not pushing everyone enough.
Yeah.
So Paul, do you want to talk a little bit about the chip packaging technologies as we kind of go forward that may help?
Yeah, I mean, I think it's all going to be incremental. There's no low-hanging fruit. It's all very hard from here. You're going after the 0.001 kind of thing. So
Right.
I don't think
get that flat. Yeah.
I don't think we transition to this idea that you have fluid directly on the die. I mean, that's great. I don't have any TIM.
Yeah.
But that's a whole packaging nightmare. I think it's going to a lot of small changes. We've done a lot on these thermal materials, right? Especially TIM 1. Going to these like more liquid metals and trying to get that bond layer optimized across tolerances. And so I think it's a lot of small things on how's that die stacked up? How are you thinning the die? Are we doing kind of XY enhancement? That helps a lot in terms of thermal conductivity on the die. What can we do in that space? But again, it's nothing that it's all going to be a lot of things that we got to go all work together with trade-offs. It's going to be harder to consume these.
That's interesting. Okay, all right, great. I appreciate that. That was all good stuff. We still have a couple of minutes left over, so we're happy to open this up to the crowd. If you guys want to ask some questions of the panel, you can take advantage of it. Yeah, if you'll come over and talk to the microphone so that the video can hear your question.
Hi, my name is Stijn de Kruijf. I have a question for the temperature. I really like what you're doing, future-proofing data center facilities, because it's CapEx investment. I'm from the design of the facilities, so 30 degrees is a great figure. Then we have a point to hit. And then it's all about how much time of the year is 30 and what's the resilience requirement around it. Is it 99.9% of the time 30 or? Because there's a lot of CapEx investment going for the 0.1% of the time.
Right. Yeah. That's a great question.
Yeah.
Right? It can always be 30 C if you run your chillers all the time, right? This is a trade-off that we look at all the time. It's like, how much trim chiller do you need, for a particular climate to, hit 30 most of the time. And then in these data centers are hundreds of thousands of square feet. So what is 30 C? Like, there is going to be variance on the data center floor for a bunch of different reasons. So this is a kind of a big trade-off that we look at. And we're really running these ML systems right to the limit. So, we need to balance the risk of throttling the chips, how many chips would throttle, what are the consequences of that, how frequently does it happen. So these are all kind of interesting trade-offs that we look at when we think about these large-scale clusters.
Yeah. I think too, we're saying 30 degrees C at the server chip, because we're also trying to look at it from the perspective of we don't want the chip vendor to really require anything lower than that. We're trying to say, okay, you guys, that's your bound. Like, we don't want you to require anything low, but at the same time, maybe we get performance out of, if we can lower that temperature a little bit. So from the data center side, we say, okay, we don't want to go any higher than that because we set the limit. But at the same time, if the water temperature is a little bit lower, especially based on your environmental conditions where you're putting the data center, that may not be a bad thing, like maybe you get a little bit more performance out of that. Maybe you can still run at a lower temperature very economically if you're in a colder weather climate. So there's nothing wrong with that, but at the same time we want to sort of have the dividing line to sort of keep both of those on each side of that line. So.
And to Chris' point, you can power management. So if it goes above, you power management down, and that is very effective for a short window. And then it's very nonlinear. So you start seeing really dramatic performance impacts versus more than 10% power management. So you don't want to get it. You can definitely manage it. You're not going to shut down, but at some point you're going to start seeing performance impacts that higher.
Yeah, and these systems are so expensive that impacting that performance is tough. The other thing I would say is the build out of these giant clusters is still a work in progress. So if you're doing it right and your schedulers are working properly, you're going to see a lot of synchronized chips hitting the maximum power all at the same time. So we need to think about, how does a giant cluster work when we can't count on it all being variable across a large space.
Definitely challenges your power infrastructure. That's what I've seen. You can create our power supply.
Thanks. I also like the view of Kelsey. If the data center can deliver for free lower temperatures, then it adds up. But then you have to start communicating between IT and the facility. That you raise your hand as IT, saying, okay, if you can do that, make it.
Yeah.
Thanks.
Sure, you bet. That's a good question. Anybody else? Yeah.
John
Hey,
Gross
John
with JM Gross Engineering. So this question is really kind of directed at Paul. So you referred earlier to the secondary temperature classes that are coming out in the book. And my understanding from our conversations, because I've worked with you on TC99, is that the end game is that much like the air classes turned into server manufacturers publishing, we're manufacturing the server to operate in an A1 or an A2 environment. The same thing is intended to happen with the server manufacturers with these new secondary loop temperature classes.
Exactly. Yeah. You want to have a common point between the manufacturer and the consumer.
Right, so now we're finally bridging the gap from the FWS to the silicon, and so we can say, okay, we've designed a facility where the FWS is maybe designed for W27, the TCS is designed for an S30, and then as long as the owner brings in and installs S30 class servers or higher, then they're good.
Exactly.
All right. Great. I think that's about all the time we've got. So thanks to the panel for a good discussion. So really appreciate it.
Thank you all.
Thanks.